Can you hear me? Okay, today I'm going to talk about one topic that I've been working on for the past year or so. It's using a regional version of GSM, which is my model, to look at historic extreme events and understand precipitation and flood risk. So this work funded mostly by NSF and also by James Kinter from Virginia. So some of you probably know about my model that called System for Atmospheric Modeling, or SAM. And over the past several years, it grew up into a global version on latitude-longitude grid. It's a pretty versatile model. It's finite difference dynamical core. It has pretty good numerics. It considers not only momentum, of course, but also kinetic energy, which is important for global simulations. It has a variety of physical packages, different microphysics schemes, two radiation schemes, and also land surface model with interactive soil and vegetation developed by my former student, graduate student, Jun Lee. It turned out to be a very good land surface model. And also it has topography, which is a box fill kind of representation on, so it's not terrain following topography, it's actually can simulate buildings, for example. And it's massively parallel using pure MPI. So what I've been doing over the past year or so is trying to create a regional version of that model. The motivation is clear. This global model simulation shown here, it's very expensive to run. For example, Diamond simulation, which is 40 days, a global Diamond is a project that when this global cloud resolving model intercomparison project, 40-day simulation takes about 1 million core hours. So it would be very difficult logistically and just in terms of storage to do all the sensitivity studies, testing microphysics, changing microphysics, this and that. So I thought that maybe it's good to have some kind of regional version of that. So over a smaller domain, and and it's turned out to be not that simple task. It's not open boundary conditions. It's slightly different thing. Finally I succeeded, and so basically the idea is that I use I don't remember how it's called. I think it's like Davis method, which is nudging boundary conditions along strips, like around the domain, like 5% on each side. It sounds simple, but actually implementation is not that simple, because especially for an elastic model. And then, of course, there is optional nudging inside the domain if you want to nudging or relaxation to reanalysis. So boundary conditions are from era 5 reanalysis, and you can optionally also nudge inside domain, but most simulations that I will show, they don't use internal nudging. So inside the domain, it's completely free run. Only boundaries are nudged or forced, model forced into the solution of a certain domain. So I've been applied it to almost 10 different hurricanes, one nor'easter, one atmospheric river so far. And some of the simulations I'm gonna show. So the main purpose of this project is actually to simulate extreme events with high resolution of 1 to 3 kilometers or so, and replay them, and then change environmental conditions that can be due to climate change or something, and replay the same event to see how that event would look like in the future. So that's main motivation. And also, this model is very good for testing and improving the various aspects of model, because it's very cheap to run. So the first example I'm going to show, it's atmospheric river in October of 2021 over California. that was record-breaking atmospheric river. It produces a huge amount of rain in the Bay Area. It's classified as category 5 or exceptional atmospheric river. So it was nice to simulate. So on the right, so the domain was 3,000 by 3,000 kilometers with 1 kilometer grid spacing. It takes about, this is a relatively expensive run, it takes about 9-10 hours of wall clock hours to simulate, or to simulate period from October 21st to October 27th using 3,000 cores. So on the right, it's the top visualization is precipitable water or total column water vapor from the model, and at the bottom from ERA 5, or basically reanalysis or observations. So if you can see that inside the domain there is no nudging. So there is no nudging inside the domain. You can see that it's very close, reproduces circulation over Western United States, that it's actually sometimes difficult to tell them apart. So again, there is no nudging in the middle of the domain. Another example is Hurricane Helen last year, less than 1 year ago. This hurricane was not very strong one, but it, as you probably remember, it produced a lot of flooding in over the Carolinas. So it's started somewhere in the Caribbean Ocean, and so I initialized it on September 24 and ran it for like 5 days or 4 days or so. The domain in this case was smaller. It's 1,000 by 1,000 grid cells, but resolution was coarse, 4 kilometers. So that's basically the same resolution which is used in global model. So that was the motivation, just to use the same resolution to check the numerics and physics. And again, no nudging is done inside the domain. So this is simulation. So the top is model, and the bottom is ERA 5. And look how ERA 5 is jerky, because it's reinitialized every day or so. So basically following observations. And my model, of course, is not. So it still is kind of very close, close follow each other. But if you look at the tracks, so I ran ensemble, generating ensemble using ERA 5 ensemble. So ERA 5 dataset has 10 ensemble members in it. So I use that for initialization of the model, but boundary conditions still reanalysis. And here I just demonstrate sensitivity to microphysics. I used like 4 different microphysical packages. A standard microphysics is that using global model is same one moment, single moment microphysics, very simple, very fast. And the rest are much more comprehensive microphysics, but they're expensive, like P3, Morris in 2005, and Thompson. And you see the tracks that, well, all 3 microphysics that more comprehensive produce inferior simulation compared to simple one moment microphysics. That kind of was interesting. And maybe it's not so surprising, because as far as I know, the WRF that used for hurricane simulation uses single moment microphysics, because it produces superior results. Now, another hurricane is Milton. And Milton, it was interesting hurricane. It was last year, over Caribbean hurricane. It's category 5. It developed into category 5 in the Gulf of America. So Gulf of Mexico, America, and that's very rare in the Gulf. It's not that common. So so it was interesting to see. And one of the things about this hurricane, it's developed into category 5 from tropical storms in the matter of a couple of days. So it was very fast, rapid intensification. Domain in this case is the same as for Hurricane Helen, but I also did one simulation with 1 kilometer, 1.33 kilometer grid spacing instead of 4, but domain size is the same. And again, no internal nudging was used. And for these simulations, which is like 5 or 6 days, it runs about, it takes only 2 hours to run. So you can run ensembles very easily. So here, what I'm going to show, like on the right, there is some tracks, and track is not well reproduced, but the main point of this was the intensity and time evolution. So on this figure, yeah. So this plot shows horizontal axis is 10-meter wind speed. So this is basically maximum wind speed. And vertical axis is surface pressure. So you can see that, so observations are black dots. It's from best track. And all these ensemble members, total 11 members, you see that they pretty closely match this kind of relationship between maximum wind speed and observed relationship between maximum wind speed and pressure. Now, in terms of time evolution, this is the time, horizontal axis time here. This is 10 meter speed. So you see that starting at on October 5, it was barely, it was tropical storm. It was not even hurricane. And observations suggest that by October 8, it was already category 5 hurricane with very strong winds up to almost 80 meters per second. And so you see that this is different members or ensemble members. So you see that it depends how you initialize it. And and this is pressure. So model is not very well, does not reproduce this intensification quite well. And then I tried higher resolution, which is 1.33. And in that case, this is the this is coarse resolution, so it's 8 kilometer grid, and you see that there is no strong hurricane at all. All members generate pretty weak hurricane of maybe category 3 maximum. So resolution does matter, but when I switch to much higher resolution, it's almost perfectly reproduced. It's category 5, and this is evolution of maximum wind relative to observations, and this is pressure. The only thing that it didn't reproduce is this event, which was eye replacement cycle here, but it's pretty random event. And but overall, the evolution, the intensification, reproduce almost perfectly. And again, it's no nudging was done. And now this is Agnes, Hurricane Agnes, which was 1972. Why I chose this hurricane, which caused catastrophic flooding in Pennsylvania and Virginia back then. And it was not strong hurricane at all. It was category 1 hurricane. But by its trajectory, it's, you see, starting in the Caribbean again. I mean, in the Gulf of America, and then went to here. And I don't know how to call it. So simulation was pretty good, but now the point of the simulation, because it was 1972, since then there has been actually climate change. And so it was interesting to see how this same hurricane would, what rain it would produce if it happened today or last year. So I looked at the data, and this is pretty amazing actually. I think this kind of images should be shown on CNN or something, because people will like say, oh, there is no global warming, like it's all made up. Look at this. This is mean June surface temperature, average over 5 years from 68 to 72, and difference between like today from 2020, 24. And this is difference. And look at these colors. Like this Europe, for example, it's 3-4 degrees change in June, average June. That's no wonder they have these heat waves all the time, right? And over US, like it's mostly Canada, but like if you look at Gulf of Mexico, you see that it's it's something like almost 1 degree warming on average. And this is not model, this is observations. This is over like, what, 50 years period. And this is also precipitable water. And you see that in terms of water vapor, in the Gulf, it's increased by about 5 millimeters of water. This is immense amount. 5 millimeters more water, when average is something like 50, 40, 50. So that's about like 10% increase.
So Marat, are you?
Yeah, I'm almost done. So I looked basically, so I ran this hurricane, and this is the main results is for Virginia, for example, where a lot of flooding happened. So this is in 1972 map of precipitation accumulation, and this is if it happened today. And the increase, if you look at percentage, relative change, you see it's about 30–40%. And in mountains, it's like 80% increase of rain. And that flooding was already catastrophic back then. So now it would be like 30–40% even more, right? So that's concerning. So this model can be downloaded by anybody, especially like students. It's very easy to set up, very easy to run. It has a user manual. It has I have YouTube channel that actually has detailed video instructions how to download it and set up all the boundary and all data set. So you could run any of those cases yourself. Thank you.
Really quick,
Yeah, quick question. This is very nice that you make your model with this capability. In the regional climate community, many people do similar work using the WRF. Have you compared the results of your model with people using the WRF model?
Not
No.
yet.
Okay.
This is ongoing work. It's still.
Okay.
that would be interesting.
Yeah.
Well, we got to keep moving here. So thanks, Marat.